In the quiet between galaxies, an invisible architecture shapes everything that shines. Spiral arms turn too fast. Light bends where nothing seems to be. The oldest glow in the universe carries faint clues locked into delicate patterns. Tonight, the evidence for dark matter unfolds in calm steps, from galaxy rotation curves to gravitational lensing, from the cosmic microwave background to the leading candidates still under debate. If this journey feels worth returning to, tap like and subscribe to Space Dreams documentary. Settle in now. The universe is wide and the answers arrive gently. A spiral galaxy turns with a steadiness that feels too calm to question. The outer glow does not slow as distance increases, and that stubborn speed points to hidden mass beyond the light. In that region, a thin disk of stars and faint dust lanes forms a broad luminous pinwheel. Dark gaps cut between brighter arms. The whole shape looks like a slow whirlpool of starlight layered in rings that fade toward the edge. The inner parts complete their paths on shorter timescales. The outer parts take longer, yet the measured pace of the outer orbit stays unexpectedly high. Light behaves as a messenger of motion. When an object moves, its light shifts very slightly in colour. A signal would carry that shift across empty space. From that shift, a speed can be inferred without touching the source. In the inner disk, the speeds rise quickly, then reach a plateau. Farther out, the plateau persists instead of dropping away. A gentle pattern emerges. The brighter regions do not contain enough matter to hold that pattern alone. The first quiet unlock arrives in the contrast between expectation and result. If most mass sits where light is strongest, outer orbits should slow as the luminous density thins. A galaxy should behave like a system with weight concentrated near the centre. The farther ring should feel less pull. Its speed should ease down. That easing does not arrive. The outer ring keeps pace. It traces a kind of refusal that repeats across many spiral systems. A second scene drifts into focus. A faint band of stars marks the mid-plane. Above and below it, the glow becomes thinner. At large radius, the light is sparse. The dark between arms grows wider. The disk looks fragile there, as if the visible material is running out. Motion does not share that fragility. The same steady orbital speed holds in the dim outskirts. The next unlock appears as a separation between brightness and gravity. Light maps one distribution. Motion maps another. The mismatch is not subtle. It is smooth, consistent, and hard to dismiss as noise. A single number can hold the scale without sharpening the story into arithmetic. A typical outer orbital speed is about 200 kilometers per second. That is enough to circle an Earth-sized planet in a few minutes. The comparison is only a bridge. The key detail is that such speed persists where the visible matter is thin. The physical picture is not a dot of mass in the centre. It is a wide influence that extends well past the bright disk. The best simple description is a halo. A halo is a roughly spherical envelope of mass around a galaxy. It is not made of visible stars in any matching amount. It is inferred from what the stars and gas must be doing to remain in orbit. The river analogy arrives gently. Imagine a broad river whose surface looks calm. Near the centre, one might expect faster flow. Near the banks, one might expect slower flow. The surprise is a current that stays nearly the same from centre to edge. The surface gives no obvious hint of an invisible guide beneath. A channel carved deep and wide can hold a steady flow even where the surface appears shallow. In the same way, a galaxy can keep outer speeds high if a deep gravitational channel extends far beyond the bright parts. The analogy does not claim identity. It offers a shape of intuition. Gravity does not push like water. It binds like a curve in space and time. Still, the sense of a hidden depth helps the mind rest. Another slow visual anchor returns to the galaxy itself. The arms are not rigid structures. They are patterns in a rotating disk. Stars drift through them. Gas compresses and spreads. Dust bands thread along the inner edges of bright lanes. At the outskirts, the disk becomes more transparent. The arms lose contrast. The galaxy's boundary looks like a gradient rather than a wall. Motion continues past that gradient. It is as if the orbiting material follows a map that the light cannot draw. The next unlock sits inside that word map. Mass is what shapes the gravitational potential. The potential is the landscape in which orbits settle. A shallow landscape would let outer material drift away. A deeper landscape keeps orbits bound. The depth required by the outer speeds implies more mass than the stars and gas provide. The added mass must be distributed broadly. It must grow with radius over the region where the light fades. That is what a dark halo accomplishes. It supplies mass without adding matching luminosity. It changes the relationship between radius and orbital speed. The calmness of the evidence is part of its power. It does not rely on a rare event. It relies on regular motion. It relies on equilibrium, or at least on long-lived patterns. That regularity supports a stable inference. If the same shape appears across many galaxies, a common cause becomes likely. Another visual anchor arrives as a series of concentric rings imagined within the disk. Each ring holds a different orbital period. The inner rings complete a circuit on timescales closer to tens of millions of years. The outer rings stretch toward hundreds of millions of years. The scale shift is soft. A color shift in light can be detected in moments. The orbit that creates the shift unfolds over epochs. The measurement is brief. The motion is ancient. The quiet bridge between them is physics that does not care about time spent waiting. The same rule links a small shift in light to a large path in space. A limit of intuition appears here, and it deserves a gentle name. Intuition expects weight to follow brightness. That expectation comes from daily experience. It comes from firelight and sunlight. It comes from objects whose visible substance is most of their mass. Galaxies do not grant that comfort. Much of their mass does not shine. Another limit is observational. The outer disk is faint. The light there is thin and noisy. Small shifts can blur into uncertainty. Gas can move in complex patterns. Orbits can be slightly non-circular. The line of sight can confuse true speed with projection. These limits can soften any single measurement. They do not naturally create the same flat pattern again and again across different systems. The repeated plateau survives careful correction. It survives changes in viewing angle. It survives different choices of traces, including gas and stars. The result remains steady enough to demand an explanation. The next unlock is that the evidence is not a claim about one object. It is a claim about a law-like regularity. When luminous density drops with radius, the needed mass does not drop as quickly. The gravitational influence remains large. This implies a mass component that extends beyond the bright disk. It also implies that this component is dominant at large radius. The stars become test particles in a broader field. The dust lanes and bright knots become small details riding on a deeper structure. Another slow scene forms at the edge. The background is darker. The arm pattern dissolves into a sparse field. A faint diffuse glow lingers like mist around the disk. The boundary is not sharp. It is a taper. The sense of a hidden envelope becomes easier to hold when the edge is seen as a fade rather than a cut. The halo in this framing is not a ring or a shell with a hard border. It is a smooth distribution that continues outward. Its density declines slowly. Its total mass within radius still rises as radius grows over a long range. That rising mass can sustain the flat rotation curve. Rotation curve is the graph of orbital speed versus distance. The definition is simple. It is the record of how fast material moves at each radius. The analogy returns as a calm tool. It is like tracing the pace of leaves at different distances from a river's centre. The record reveals the hidden depth of the channel. The Y is immediate. The record reveals the mass distribution that light cannot show. The section ends with a gentle settling. A spiral galaxy offers a steady pattern. The pattern links faint outer rings to a broad hidden halo. The next step is to turn the galaxy edge-on and let the layered structure of light and gravity separate more clearly. A galaxy is seen from the side and its bright midline looks almost too thin to carry so much weight. The edge-on view shows that the light forms a slender layer, while the gravity implied by motion spreads far above and below that layer. In that region, the disk becomes a narrow band with a sharp central ridge. Dark lanes cut through it where dust thickens. The glow fades upward into a softer haze. The boundary is not a wall. It is a gradient that thins into near black. The scene feels like layered fabric held flat in calm air. The first small unlock comes from simple geometry. When the disk is viewed edge-on, its thinness becomes obvious. The light is confined. The structure is flattened. If mass followed light closely, the gravity would also be tightly flattened. The outer motions would then depend strongly on that thin plane. Yet the orbital speeds inferred in many disks remain high at large radius. The implication is a broader mass distribution that does not share the disk's thin profile. A halo naturally matches that need. The halo is not a sheet. It is an extended envelope that surrounds the disk in 3 dimensions. A slow visual anchor returns to the dust itself. Along the midline, the dust lane looks like a dark river of shadow. It bends slightly with the disk. It thickens near the centre. It thins toward the outskirts. Small knots appear as darker beads. The lane marks where gas gathers in a compressed layer. It also marks where light is absorbed and scattered away. Light behaves as a tracer of structure, but not a complete tracer of mass. A second unlock arrives from what the dust hides. Some of the luminous mass sits behind that shadow. Some of the luminous mass is dimmed into invisibility along the line of sight. Even when the brightness is corrected, a limit remains. The outer gravitational pull is too large to be explained by the visible disk alone. The edge-on view sharpens the contrast between a thin luminous layer and a deep gravitational field. The analogy shifts to something quiet and natural. A seed can look small and simple on the outside. Inside, a dense core carries much of the weight. Around it, a light husk spreads outward with little substance. In a galaxy, the bright disk is like the visible surface layer. The broader halo is like the unseen mass that extends beyond the obvious boundary. The analogy clarifies one point immediately. Most of the influence can come from what is not bright. Another visual anchor forms as faint starlight above the disk. The glow is not symmetrical in every detail. One side looks slightly thicker where dust is less severe. The other side looks sharper where the shadow lane is darker. The light above the plane falls off smoothly. It does not break into a clear edge. That smooth decline hints that the disk is embedded in something larger. Even the luminous component has a vertical structure. It has a thin layer and a thicker layer. The next unlock is that gravity also has a vertical structure. If the mass were mostly in the thin disk, the gravitational pull toward the plane would be very strong near the plane and weaken quickly with height. A broader halo changes that. A halo adds a gentler pull that remains significant even above the disk. The overall field becomes rounder. Orbits and gas layers respond to that roundness. A single number can hold the geometry without turning it into a diagram. The bright disk is often about 100 times wider than it is thick. That is like a wide fog bank spread across a lake where the layer is shallow compared to the span. The comparison is only a shape. The point is that a very thin luminous layer cannot easily account for a gravitational influence that behaves as if it extends in all directions. The scale shift is soft. The thickness of the bright layer is a small fraction of the full diameter, yet the gravitational reach implied by outer motion stretches far beyond the visible edge. The mind moves from a thin line to a vast envelope without strain. A new term can appear briefly with care. Mass distribution means where matter is located in space. A smooth distribution produces a smooth pull. A clumped distribution produces local variations. The Y is immediate. The observed motions look smooth at large scales. That smoothness suggests a large-scale mass component that is also smooth. A halo fits that description more naturally than a disk alone. Another visual anchor arrives in the outer disk where light is sparse. The midline becomes a faint ribbon. The dust lane breaks into thin streaks. The brightness declines into a soft taper. The outermost regions look delicate, as if a gentle disturbance could unravel them. Yet the orbits remain bound for long times. The next unlock is about stability. Bound orbits over hundreds of millions of years require a steady gravitational well. A thin disk of visible matter can form such a well near the center. Far out, the disk becomes too light. A halo supplies the remaining depth. It keeps the outskirts from drifting apart. It does so quietly. It does not need to announce itself with light. A limit of observation enters here with a calm edge. Edge-on views are difficult because projection compresses 3 dimensions into one line. Light from many radii overlaps. Dust absorbs unevenly. The true shape of motion can be blurred by the line of sight. Gas can also have vertical motions. Those motions can mimic changes in rotation. Another limit is model-based. Separating the disk's mass from the halo's mass involves assumptions about how stars are distributed and how gas contributes. Different assumptions can trade mass between components while still fitting the same motions. This degeneracy is a real boundary. It means the halo cannot be weighed in perfect isolation from the disk using rotation alone. Even so, the broad conclusion persists. Under many reasonable assumptions, the disk does not provide enough mass at large radius. The halo remains required to explain the flatness of the outer speeds and the vertical balance of material. The next unlock is that multiple kinds of evidence can be prepared from this same geometry. The edge-on view does more than show thinness. It sets up a way to test how gravity behaves above the plane. Gas layers have thickness. Star layers have thickness. If gravity were only from the disk, those layers would compress more tightly near the plane. A broader field allows thicker layers without dispersing them entirely. The thickness of those layers becomes an indirect measure of the gravitational pull. That pull points again to an extended mass component. Another visual anchor settles on the halo as a concept rather than a picture. The disk is a bright flattened sheet. Around it, an unseen volume is imagined as a gentle gradient of density. It is densest near the center. It thins outward without a sharp boundary. It surrounds the disk above and below. It surrounds it in front and behind. The disk becomes a luminous slice inside a larger, darker structure. The scale shift returns once more. A tiny color shift in light can reveal motion in moments. The gravity shaping that motion holds steady across epochs. The disk rotates many times. The halo remains shaping the same curves long after individual stars drift onward. The section ends by easing forward. The edge-on view clarifies that light is thin and gravity is wide. The next movement turns to variety across galaxies where the same hidden pattern appears in different forms. A faint galaxy can look almost empty, yet its outskirts still move with the same steady confidence. The repeated pattern across very different galaxies shows that the hidden mass component is not a special case, but a common structure. In that region, the light is so diffuse that the boundary seems to dissolve before it ends. A soft oval glow sits against a darker background. Small knots of brightness appear like scattered islands. Between them, long stretches remain dim and smooth. The disk is present, but it is understated. The physical detail that stands out is the gradient. Brightness falls away gently rather than sharply. The first small unlock comes from how little light is needed to reveal the same motion. Even when the visible disk is thin in brightness, the outer speeds do not collapse. The record of motion stays flat, far from the center. That means the extra gravity is not merely correcting small gaps in starlight. It dominates the outskirts in systems where starlight barely contributes. Another slow scene forms around the midline. The gas layer extends beyond the visible glow. It makes a broader, fainter skirt around the galaxy. The outer edge is warped slightly like a thin sheet that lifts at one side. The warp is gentle. The motion through the warp remains ordered. The next unlock is that gas not only stars traces the same gravitational field. Where stars are sparse, gas can still orbit in wide rings. Those rings still demand mass distributed well beyond the bright core. A single number can hold the contrast without turning it into a ledger. In some of these dim galaxies, the total mass needed is about 10 times the mass suggested by the visible glow. That is like a shallow layer of mist riding on a much deeper blanket of fog. The comparison is only about proportion. The point is that the unseen component can outweigh the luminous component by a wide margin. This is not a subtle adjustment. It is a structural difference. Another visual anchor arrives in a different kind of galaxy. A barred spiral is seen from above. A straight band of brightness crosses the center. 2 arms spring outward from the ends of that bar. The bar looks like a bright bridge. The arms look like curved tracks that loosen as they widen. Dust lanes thread along the inner edges. The disk is richer in contrast than the faint galaxy, yet the outer orbital behavior still settles into a similar plateau. The next unlock comes from variety. A galaxy can be bright and structured, or dim and smooth. It can have a bar or lack one. It can be rich in star-forming knots or nearly free of them. The outer speed pattern still appears. This suggests the mass component shaping the outer field is not built from the same material that shapes the visible features. Spiral arms and bars are patterns in a disk. A halo is a deeper distribution that remains even when the disk's details change. The analogy shifts to a calm coastal image. Different bays have different shorelines. Some are narrow and steep, some are broad and shallow. Yet the tide rises and falls with the same slow rhythm along each coast. The shoreline shapes the local foam and eddies. The tide sets the overall timing and range. In the same way, different galaxy disks shape local brightness patterns. The extended mass sets the broad gravitational rhythm of the outskirts. The analogy does not claim identity. It offers an intuition that stays gentle. Another slow scene returns to the faint galaxy, but from the side. The midplane is hard to define because the light is weak. The whole body looks thicker, less neatly layered. A slight asymmetry appears. One side is more extended. The other side fades sooner. The physical detail is the soft edge. There is no crisp line. The galaxy looks like a dim cloud with a brighter center and a long taper. The next unlock is that even when shapes are messy, motion can remain clean. Orbital speeds can be inferred from light that shifts slightly and from gas that emits at specific wavelengths. The details of brightness can be irregular. The underlying gravitational field can still be smooth enough to guide long-lived orbits. This smoothness is a clue. It suggests a mass component with a broad, gently varying density. A halo naturally provides that. The scale shift arrives without strain. A tiny shift in a spectral line can imply motion across tens of thousands of light-years. The measurement is delicate. The orbit is immense. The timescale of a full circuit in the outer disk stretches across hundreds of millions of years. Yet the inferred speed is stable enough to compare across many galaxies. That stability makes the evidence feel quiet and firm. Another visual anchor appears in a dwarf irregular galaxy. The shape is not a classic disk. It is lopsided. Bright patches cluster on one side. A faint envelope extends on the other. The outer gas forms a broad, uneven ring. The ring is not perfectly centered. It is slightly offset. The motion around that ring still shows a broad plateau rather than a steep drop. The next unlock is that even without a neat spiral form, gravity still behaves as if an extended mass distribution is present. This matters because it weakens explanations that rely on special disk features. A bar cannot be the cause because galaxies without bars show the same pattern. Spiral arms cannot be the cause because irregular galaxies without arms show the same pattern. A thin, luminous disk cannot be the cause because diffuse systems still show it. The common element is the need for an unseen mass component that extends outward. A limit of observation enters here with a soft boundary. Very faint galaxies challenge measurement because the light is weak and spread out. The signal can be noisy. Background contamination can blur the edge. Gas motions can include turbulence and non-circular flows. A warp can tilt the outer rings. Projection can turn true speed into a smaller apparent shift. These are real limits. They mean the outermost points can carry uncertainty. A second limit is interpretive. Different assumptions about how mass is distributed can fit similar motion records. A slightly denser center with a slightly lighter outer halo can mimic a different arrangement. This is a limit of inference, not of curiosity. Even within those limits, the broad conclusion persists. Across many galaxy types, outer motion implies more mass than light provides. The next unlock is that the diversity itself becomes evidence. If the same hidden component is needed in systems with very different visible structures, then the hidden component is likely fundamental to how galaxies exist. It is not an afterthought. It is not a rare ingredient. It is a main part of the architecture. Another visual anchor settles on a quiet comparison across the sky. One galaxy is bright with sharp arms. Another is faint with a smooth glow. Another is irregular with patchy knots. Each sits within a larger unseen volume where gravity remains strong beyond the visible edge. The disk features differ. The outskirts behave in a related way. The section eases forward. When a galaxy is not alone, smaller companions drift through the same extended field. The next movement follows those companions where orbital paths become another calm measure of hidden mass. A small companion galaxy drifts through darkness, and its path quietly sketches the gravity of a much larger host. The way these companions move shows that mass extends far beyond the bright disk shaping orbits, at distances where starlight is thin. At this distance, a large spiral appears as a pale disk with a brighter core. Around it, the background is deep and still. Off to one side, a smaller smudge of light hangs like a faint ember. A thin stream of stars trails behind it. The stream is not straight. It curves in a long arc, then fades into a powdery haze. The physical detail is the arc itself. It marks where the companion has been stretched by tides. It also marks the direction of the gravitational pull that guides it. The first small unlock comes from a simple idea. A bound orbit needs a gravitational well that reaches out to the orbit's size. If the host's mass were mostly confined to the bright disk, the pull far away would weaken quickly. The companion's orbit would loosen. Its stream would not wrap so cleanly. Yet many companions remain bound on wide paths. Their streams bend as if they're tracing a larger rounder field than the disk alone can provide. A slow visual anchor settles on the stream. It has a braided look in places. One strand is brighter. Another is thinner and more diffuse. The brightness changes smoothly along the arc. The width broadens where the stream disperses. The tail's outer edge is feathered like a soft brush stroke. The next unlock is that the stream is a memory of motion. Individual stars in the stream do not travel as a solid rope. They spread along slightly different orbits. That spread is controlled by the host's gravitational potential. Potential is the shape of gravity in space. A smooth potential produces smooth, coherent arcs. A patchy potential would tear the arc into sharper kinks. The observed curvature suggests a broad, gently varying mass distribution. A halo fits that requirement. The analogy shifts to something quiet and familiar. A floating leaf can reveal a slow whirl in a pond even when the surface looks calm. The leaf's path curves where the water's depth and flow guide it. The leaf does not create the whirl, it only traces it. In the same way, a companion traces the hidden structure of gravity around a host. The analogy carries one immediate meaning. The tracer is small, the field is large. Another scene moves closer to the companion itself. Its light is uneven. One side is brighter, the other side is stretched into a dim extension. The core is slightly offset from the center of the glow. The shape suggests ongoing stripping. The host's tides pull harder on the near side than on the far side. This gradient in pull is what draws out a tail. The next unlock is that tides depend on how gravity changes with distance. A steeply declining field would produce a different stripping pattern than a broad halo. In a halo-dominated region, the gravitational pull declines more gently with radius. The tidal forces remain significant over a long range. That can produce extended, graceful streams rather than short, abrupt plumes. A single number can hold the scale without demanding precision. Some of these streams stretch for about 100,000 light-years. That is like a ribbon that could span the full width of a large galaxy several times. The comparison is only about length. The key point is that the gravitational influence must remain coherent over that span. The companion's debris does not drift randomly. It follows a curved track that stays organized for long times. Another visual anchor appears as a series of faint shells around a larger elliptical galaxy. The shells look like stacked crescents. Each is a thin edge of enhanced brightness. Between shells, the glow is softer. The edges are sharp, then they dissolve outward. The physical detail is the sharp rim. It marks where many stars in the debris reach similar turning points in their orbits. The next unlock is that turning points are sensitive to the potential shape. If the mass were concentrated tightly, the turning points would sit closer in. If the mass extends outward, the turning points can occur farther out and in a repeating pattern. These shells become quiet contour lines of gravity. They are not drawn by instruments. They are drawn by dynamics over long times. The scale shift settles in. A faint edge in the shell is visible as a delicate line. The orbit that creates that edge can take hundreds of millions of years. The brightness pattern can be seen in an instant. The gravitational choreography behind it unfolds across epochs. The contrast between quick perception and slow cause makes the evidence feel calm and deep. A limit of observation enters gently. Streams are faint. Their surface brightness can fall close to the background. Confusion with unrelated background objects can blur their true extent. Projection can also mislead. A stream can appear denser if it lies along the line of sight. It can appear shorter if it lies across it. Another limit is model-based. Reconstructing an orbit from a stream requires assumptions about the companion's initial shape and internal motions. Different histories can produce similar arcs. This is a limit of inference. Even with that uncertainty, the broad requirement remains. To keep wide orbits bound and to shape long arcs and shells, the host must have mass extending far beyond the bright disk. Another small unlock comes from comparing different companions around the same host. Some orbit in one plane, others tilt. Some pass closer to the center, others loop farther out. The host's halo must guide all of them within one gravitational field. If the field were dominated by a thin disk, tilted orbits would behave differently. The persistence of bound, varied orbits supports a rounder, more extended mass component. Another slow visual anchor returns to the host galaxy. The bright disk is a thin, glowing plate. The streams and shells float around it like pale smoke. The disk looks like a bright island. The debris arcs look like faint coastlines far offshore. The impression is of a system larger than its light. The halo is not seen directly, but its influence is everywhere in the curvature. The next unlock is that companions provide a lever arm. Rotation curves test gravity within the disk and just beyond it. Companions test gravity much farther out where the halo should dominate. The two lines of evidence agree in their direction. They point to extended mass that does not shine. The section eases toward the next step. If gravity can bend orbits, it can also bend light. The next movement follows light itself as it curves around mass-leaving arcs and distortions that reveal the same hidden halo in a different way. A distant cluster can look like scattered lanterns, yet the space between them quietly reshapes the light behind. The curved streaks of background light reveal gravity from total mass, not from brightness alone. In that region, many galaxies hang in a loose swarm. Between them, the background is not empty. It is filled with faint, unresolved glow from far behind. Near the cluster's center, that background glow becomes distorted. Thin arcs appear. They are pale and stretched. Their edges are brighter than their middles. Some arcs curve like crescents around an invisible center. Others split into short segments that align along the same curve. The physical detail is the curvature. It is smooth and consistent across separate streaks. The first small unlock comes from a simple shift in perspective. Gravity does not only guide orbits, it also guides paths of light. When mass is concentrated, it bends the space that light crosses. Light behaves as a traveller that follows the straightest path available. In curved space, that straightest path looks bent. A cluster can therefore act like a lens. It does not shine like glass. It bends by gravity alone. The arcs are the signature of that bending. Another slow visual anchor settles on one bright arc near the cluster core. The arc is thin like a strand. Its brightness varies along its length. One end is sharper. The other end fades into a softer smudge. The arc's curve matches the cluster's broad shape. A second fainter arc sits farther out, echoing the same center. The next unlock arrives from the matching curvature. Different background sources can be bent into shapes that share the same focal region. When multiple arcs point to the same center, the bending mass can be mapped. That mapping does not require the cluster's galaxies to be the only mass. It requires whatever mass creates the curvature. The mass inferred from lensing often exceeds the mass seen in starlight. This is a quiet return of the same story from rotation curves now told through geometry rather than motion. An analogy can hold the feeling without claiming literal identity. A stone placed under a stretched sheet creates a smooth depression. Tiny beads rolling across the sheet curve toward the lowest part. The beads do not know the stone. Their paths reveal the shape of the depression. In the same way, light paths reveal the shape of gravity. The analogy clarifies one point immediately. The visible surface does not need to show the cause. The path reveals it. Another visual anchor widens the scene. Several arcs appear at different distances from the center. The inner arcs are brighter and thinner. The outer arcs are fainter and longer. The cluster galaxies themselves look like small islands of light. Their halos overlap in projection. The background is soft and grainy. The arcs stand out like delicate brushstrokes laid across that grain. The next unlock is that arcs can indicate strong lensing. Strong lensing occurs when the bending is large enough to stretch images into long curves. The condition for this is a deep gravitational potential and a favorable alignment. Alignment is the positioning of source lens and observer along nearly the same line. Even without speaking of any observer, alignment can be described as one line of sight passing close to the center of mass. When the geometry is right, a background galaxy can appear as an arc rather than a small oval. Sometimes it can appear in multiple places. Multiple images are different light paths from one source through the same gravitational landscape. The number for this section stays gentle and round. A typical arc can be stretched to about 10 times the length of its width. That is like pulling a small droplet into a long smear across a surface. The comparison is only about shape. The point is that gravity can magnify and stretch without adding light of its own. This stretching makes faint background sources easier to detect. It also makes the lensing signature more visible. Another unlock follows from that magnification. Lensing is sensitive to total mass. It does not care whether the mass shines. Stars contribute, gas contributes, dark matter contributes. All mass curves the same geometry. This makes lensing a clean test of hidden mass. Rotation curves infer mass from motion. Lensing infers mass from bending. The agreement between them is powerful because the methods are different. One method listens to orbital balance. The other reads spatial curvature. Both point toward more mass than light accounts for. Another visual anchor becomes more detailed near the cluster center. A bright galaxy sits there with a smooth, rounded glow. Its outer light fades into a soft envelope. Around it, arcs seem to wrap like a partial ring. The edges of the arcs are sharper than the diffuse light of the lensing galaxy. The contrast between sharp arcs and soft lens light is striking. The arcs look like fine scratches on a dark surface. The next unlock arrives from the ring-like geometry. When alignment is especially close, arcs can form a near-complete circle. This is called an Einstein ring, though the name does not need emphasis. The concept is simple. A nearly circular arc pattern indicates symmetry in the lensing mass near the center. Symmetry does not mean a perfect sphere. It means the projected mass distribution is smooth enough to focus light along a similar radius. The ring is a contour of equal bending strength. It is a visual map of gravity. The scale shift appears gently. An arc that spans a small patch of sky can correspond to a physical length across tens of thousands of light years. The curvature that shapes it comes from mass spread across millions of light years in the cluster. A thin line in an image corresponds to an immense spatial arrangement. The mind moves from a delicate curve to a vast mass field without strain. A limit of observation enters with quiet clarity. Not every curved feature is lensing. Some background galaxies are naturally elongated, some align by chance. The identification of true arcs requires careful separation of shape and context. Another limit is resolution. Fine structure within an arc can be blurred when the source is small and distant. The arc's exact thickness and brightness profile can be uncertain. A third limit is modelling. Reconstructing the mass distribution from arcs is not unique. Different mass maps can reproduce similar arc positions if the map is adjusted in certain ways. This is a limit of inference called degeneracy. It does not erase the need for substantial mass. It means the exact details of where that mass sits can vary within the allowed solutions. Even within those boundaries, a stable conclusion remains. The lensing mass is larger than the visible mass. The extra component must be widespread. In clusters, that component often dominates. Another small unlock comes from comparing the cluster's light to the arc pattern. The brightest galaxies are not always exactly where the strongest lensing appears. Sometimes the lensing center is offset from the brightest spot. Sometimes the mass appears smoother than the light distribution. This indicates that the dominant mass is not simply the sum of luminous galaxies. It is a broader field in which galaxies are embedded. That field is consistent with a large dark matter component. Another visual anchor settles into stillness. The cluster looks like a slow storm frozen in place. The arcs are like pale ripples around the densest region. The ripples do not come from wind or waves. They come from gravity shaping light paths across deep time. The section ends by easing forward. Strong arcs are dramatic but rare. The next movement turns to subtler distortion spread across many background shapes where the same mass can be read in a quieter way. A wide field of distant galaxies can look ordinary, yet their shapes lean in the same quiet direction. That shared lean is weak lensing, and it reveals broad dark mass without relying on rare bright arcs. In that region, the background is filled with tiny ovals and faint smudges. Each is small and soft-edged. Most look slightly stretched, but not in any obvious pattern at first. Then a gentle order emerges when many shapes are considered together. The ovals align by a subtle preference. Their long axes tilt around the same center. The physical detail is the shear pattern. It is not a single curve. It is a slow twist in orientation across the field. The first small unlock comes from why this is useful. Strong lensing shows dramatic arcs when alignment is nearly perfect. Weak lensing works when alignment is only approximate. It does not need a ring or a bright streak. It only needs a slight consistent distortion across many background sources. The distortion is small for each object. The consistency becomes clear when the field is averaged. This turns randomness into a signal. Light behaves as a thin thread that is gently pulled off a straight line. A signal would carry that pull as a change in shape rather than a shift in color. Another slow visual anchor settles on a cluster outskirts rather than its center. The bright galaxies thin out. The sky looks emptier. Yet the background shapes still show a faint tangential alignment around the same center. The effect extends beyond where the light of the cluster galaxies is strongest. The next unlock is that the mass map can be wider than the light map. If visible galaxies were the only mass, the lensing signal would fall off quickly outside the bright region. Instead, the shear often remains measurable farther out. This indicates an extended mass distribution that continues beyond the luminous core. The halo idea, first built from rotation and companions, appears again at a larger scale. Clusters have halos too. Their halos overlap and merge in the cosmic web. Another visual anchor arrives as a faint, smooth oval region, where the shear is slightly stronger. It looks like an invisible hill in the mass landscape. Around that hill, background shapes are stretched tangentially like short strokes wrapped around a center. The strokes are not perfect circles. They are slightly irregular because the mass is not perfectly symmetric. The next unlock is that weak lensing can reveal substructure. Small clumps of mass can create local changes in the shear direction. These changes can be subtle, but they can be detected statistically. This matters because it tests whether dark matter forms clumps and how those clumps are distributed. It also tests whether the mass is smoother than the light. The method does not require the mass to shine. It reads curvature directly from the background. The analogy shifts to a quiet landscape image. A gentle wind can comb a field of tall grass. Each blade bends only a little. Any single blade could bend for many reasons. Across the whole field a pattern appears. The wind direction becomes clear. In weak lensing, the background galaxies are like blades of grass. The gravitational field is like a wind that bends their apparent shapes. The analogy clarifies the method. One object is noisy. Many objects become coherent. Another slow scene moves closer to one background source. Its original shape is unknown. It could be rounder. It could be more elongated. Weak lensing does not require knowing the original. It assumes that on average random orientations cancel out. Only a coherent distortion remains. The next unlock is that weak lensing is inherently statistical. It trades certainty about any one galaxy for a reliable average across many. This is not a weakness. It is a designed approach that fits the sky's complexity. The sky provides countless background sources. Their small signals can be combined into a clean pattern. A single number can hold the scale of the subtlety. The typical distortion for an individual background galaxy is about 1 part in 100. That is like slightly stretching a round drop into an oval that is almost still round. The comparison is about smallness. It explains why the pattern is hard to see without averaging. The effect is gentle. The evidence comes from patience and accumulation. Another visual anchor widens into a map-like impression without becoming a map. Regions of stronger shear appear as broad patches. Between patches the shear weakens. The pattern is not random. It follows the distribution of galaxy groups and clusters. It also fills in the spaces between them. The next unlock is that weak lensing can trace the cosmic web. The web is the network of filaments and nodes formed by matter on large scales. Filaments are long, faint bridges of density. Nodes are the dense intersections. Weak lensing can detect the mass in both even when the light is sparse. This links a small shape change in a distant background source to the largest structures in the universe. The scale shift arrives softly. A tiny change in an oval shape is measured in a single glance. The mass that causes it spans millions of light years. The paths of light cross that span in long travel times. Yet the distortion is delivered as a simple geometric cue. A subtle stretch contains the imprint of a vast distribution. Another unlock follows from comparing weak lensing to other evidence. Rotation curves speak to galaxy halos. Companion orbits speak to extended gravity around hosts. Strong lensing speaks to deep cluster cores. Weak lensing speaks to broader regions and to average behavior. The same dark component can satisfy all these tests. Each test has different vulnerabilities. Their agreement reduces the chance that any one limitation is misleading. A limit of observation enters with calm precision. The shapes of distant galaxies are blurred by the atmosphere of their own environments and by intervening matter. Their images are small and faint. Even a slight blurring can mimic or hide a weak lensing signal. This is a resolution limit. Another limit is selection. Only galaxies bright enough to measure are included. That can bias the sample. A third limit is intrinsic alignment. Nearby galaxies can share a preferred orientation for reasons unrelated to lensing. This can contaminate the average. These limits require careful modelling and correction. They do not create a false shear pattern that matches known mass concentrations across the sky in many independent surveys. The next unlock is that weak lensing can weigh halos without relying on light as a proxy. It can show that mass extends beyond luminous boundaries. It can reveal that the mass distribution is smoother and more extended than the visible galaxies suggest. It can also show where the mass is offset from the brightest light. This builds toward a deeper point. Dark matter is not inferred from one technique. It is inferred from a web of techniques that point in the same direction. Another visual anchor settles into stillness. The field of tiny ovals becomes a quiet sea. The coherent lean is like a gentle swell. It is not a dramatic wave. It is a calm, persistent bias that only appears when many objects are viewed together. The section eases forward. Lensing reads mass through geometry. The next movement adds another form of mass evidence inside clusters, where hot gas glows softly, yet cannot explain the full pull that lensing reveals. A cluster can glow with a soft internal haze, and that glow still cannot account for the cluster's full grip on space. The hot gas shows where ordinary matter sits, yet lensing and motion indicate much more mass than the gas can provide. In that region, a diffuse cloud fills the space between galaxies. It is not bright like starlight. It is a smooth veil that thickens toward the center. The brightness fades outward in a gentle gradient. Within the veil, darker cavities appear. Their edges are rounded. Some look like bubbles pressed into foam. Around those cavities, the haze is slightly brighter, as if compressed into a thin rim. The physical detail is the rim. It marks a boundary where the gas density changes. The first small unlock comes from what this haze represents. It is a plasma. Plasma is gas with free charged particles. It is hot enough that atoms are stripped. It fills the cluster's volume and carries most of the ordinary matter in the system. Even without any mention of instruments, the presence of this hot component can be inferred from its diffuse glow. The glow is not a decoration. It is a measure of density and temperature across the cluster. Another slow visual anchor settles on the center where the haze is brightest. The core looks smoother than the distribution of galaxies. The galaxies are scattered points. The gas is a continuous field. The gas appears layered. A brighter inner region blends into a dimmer outer region. The transition is gradual. The next unlock is that gas pressure helps support the cluster against gravity. Hot gas pushes outward. Gravity pulls inward. In a long-lived cluster, these can balance in a rough equilibrium. That balance allows an estimate of the gravitational pull required to hold the gas in place. If the gas is very hot, the pressure is strong, so gravity must be strong as well to confine it. This is a second path to mass separate from lensing. When the inferred gravity is compared to the visible material, a gap appears again. The analogy shifts to something simple and quiet. Imagine steam trapped under a broad lid. The steam presses upward. The lid's weight and seal keep it from escaping. If the steam is hotter, the lid must be heavier to hold it down. In the same way, hotter cluster gas implies a heavier gravitational lid. The lid is not a solid object. It is the total mass that shapes the gravitational potential. The analogy clarifies the logic. Pressure hints at the weight above it. Another visual anchor appears as a faint shock-like edge in the haze. The brightness changes over a short distance. One side is denser, the other side is thinner. The edge is curved like a crescent. This suggests motion and compression within the gas. The next unlock is that gas is dynamic, not frozen. It can flow slosh and form waves. These motions still occur inside the cluster's overall gravity. The gravity must remain deep enough to keep the gas bound despite stirring. This reinforces the need for a large total mass. Ordinary matter contributes, but it is not enough to shape the whole basin. A single number can hold the scale of temperature without turning the story into a table. The gas can reach about 100 million degrees. That is like a furnace that would vaporize any familiar material instantly. The comparison is about intensity. It highlights why the gas remains a plasma and why its pressure is enormous. Such hot gas cannot sit quietly unless the gravitational well is deep. The cluster's luminous galaxies alone do not create a well deep enough. Even the gas itself, despite being massive for ordinary matter, still falls short. The gap points again to dark matter. Another unlock follows from how the gas and galaxies occupy different shapes. Galaxies move like discrete bodies. Gas behaves like a fluid. In a collision between clusters, galaxies can pass through one another with relatively little direct interaction. Gas can collide, compress, and heat. This difference makes clusters a laboratory for separating components. Even without emphasizing any rare event, the everyday fact remains. Gas traces ordinary matter, lensing traces total matter. When their maps are compared, the total is larger and often smoother than the gas alone. Another slow visual anchor settles on the outer regions. The haze becomes faint and grainy. It blends into the background. A subtle elongation appears. The cluster is not perfectly round. It has a mild axis like a stretched oval. The gas follows that shape. The next unlock is that the gravitational potential also follows a broad shape. A halo of dark matter can be elongated. It can have substructure. It can merge with neighbouring halos. The gas responds to that potential, but it also responds to its own pressure. This means gas is a tracer with conditions. It cannot simply fall wherever gravity points. It must also satisfy hydrodynamics. That is why lensing remains valuable. It avoids gas physics and reads mass directly. The scale shift arrives softly. The gas density changes on scales of tens of thousands of light-years within the core. The cluster spans millions of light-years. The same gravity shapes both the small ripples and the large basin. The cluster's gas cools and heats over long times. The gravitational well persists across billions of years. A small brightness edge can reflect a process that unfolds slowly, yet it is held within a stable large-scale structure. A limit of observation enters with calm specificity. The gas glow depends on density squared. So bright regions dominate the signal. Faint outskirts are harder to measure. Temperature estimates can be uncertain when the signal is weak. Another limit is equilibrium. The method that infers mass from gas pressure assumes the gas is close to balance. If the gas is sloshing or shocked, the pressure support can be misestimated. This is a limit of modelling. A third limit is clumping. Small dense clumps can bias density estimates upward. These limits matter. They can change details of the inferred mass profile. They do not erase the broad mismatch between visible matter and total gravity, indicated by lensing and dynamics. The mismatch is too large and too consistent across clusters. Another small unlock comes from combining the information. Gas tells how ordinary matter is distributed. Galaxies tell where starlight sits. Lensing tells where total mass sits. When all three are placed together, a coherent picture forms. Ordinary matter is a minority component by mass. It is important for glow and structure, but it does not dominate gravity. The dominant component is dark. It shapes the basin in which gas collects and galaxies orbit. Another visual anchor settles into stillness. The cluster looks like a faint luminous fog wrapped around scattered points of starlight. The fog has cavities and rims. The points have no such fluid edges. The total gravity read by lensing is broader than both. The section eases forward. If dark matter shapes clusters and galaxies, it also shapes the earliest patterns in the universe's oldest light. The next movement turns from clusters to the background glow of the cosmic microwave sky. An ancient glow fills all directions, and its faint mottling carries the early fingerprint of cosmic matter. The cosmic microwave background preserves a snapshot of the young universe, and its pattern fits a universe where dark matter shapes gravity from the start. In that region, the sky is not truly uniform. It holds tiny variations in brightness. They are not sharp spots. They are soft patches like gentle clouding on a smooth surface. Some patches are slightly warmer in tone, some are slightly cooler. The physical detail is the fine grain. It is a speckled texture laid over a nearly even field. The first small unlock comes from what this glow is. It is leftover light from a time when the universe becomes transparent. Before that moment, light scatters repeatedly from free-charged particles. Scattering keeps light trapped like fog in a dense valley. When conditions change, the scattering drops. Light can then travel freely. The released light fills space and remains as a background glow. Light behaves as a fossil record. It carries information from the conditions at release across vast time. Another slow visual anchor settles on the boundary between slightly warmer and slightly cooler regions. The boundary is not a line, it is a gradient. It softens over a broad area. The mottling has preferred sizes. Very large regions blend smoothly. Very small regions blur into the background. The next unlock is that these variations are not noise. They reflect tiny density differences in the early universe. Denser regions pull more strongly. They influence how matter and radiation distribute. The variations become seeds. Much later, these seeds grow into the structures seen in galaxies and clusters. The connection to dark matter appears here with calm directness. Ordinary matter interacts with radiation. It feels pressure from radiation and from its own thermal motion. This pressure resists gravitational collapse in the early era. Dark matter does not interact with radiation in the same way. It can begin to clump earlier. It can deepen gravitational wells while ordinary matter is still held back by pressure. When the universe becomes transparent, ordinary matter can fall into those pre-existing wells. This helps explain how large structures form in the available time. The analogy shifts to a quiet winter scene. A shallow layer of snow can drift in wind and settle unevenly. Beneath it, hidden ground depressions guide where snow collects more deeply once the wind calms. The snow alone cannot carve those depressions, it only reveals them. In the same way, ordinary matter and light reveal the gravitational landscape. Dark matter provides much of that landscape early. The analogy clarifies the timing. The guiding shape is present before the visible filling arrives. Another visual anchor forms as ripples in a smooth pond surface. The ripples are not high. They are low and wide. They overlap gently. The mottling in the background glow resembles such overlapping ripples frozen at a moment. The next unlock is that the sizes of these ripples matter. The early universe supports oscillations in the ordinary matter and radiation mixture. These oscillations leave imprints as preferred scales in the pattern. Dark matter changes how strong these imprints are and how they relate to one another. It supplies gravity without adding the same pressure response. This changes the balance between compression and rarefaction in the early fluid. A single number can hold the timescale of this snapshot. The release occurs about 380,000 years after the universe begins. That is like looking at a forest's first morning after a long winter before any tall trunks exist. The comparison is only about youth. It emphasizes that the image is early long before galaxies appear, yet the pattern already contains the seeds and the rules that will later guide growth. Another unlock arrives from the idea of transparency. The early universe is opaque because light scatters frequently. When conditions change, the scattering rate drops, and the mean free path of light grows immensely. Mean free path means the average distance between scatterings. In the opaque era, it is small. In the transparent era, it becomes vast. The Y is immediate. This sudden change freezes a snapshot. It preserves the pattern of temperature variations on the sky. The pattern is a record of density and motion in the early plasma. Dark matter influences that record by shaping the gravitational potentials that drive the oscillations. Another slow visual anchor settles on a very large patch of slightly cooler glow. Surrounding it are smaller patches. The arrangement is not random. It has a coherence across angles. The next unlock is that the pattern statistics are precise. The overall amplitude and the distribution of patch sizes can be measured. These measurements constrain the amount of ordinary matter, the amount of dark matter, and the geometry of the universe. The point can be held without numbers beyond the single timescale already given. Dark matter is required to match the relative strengths of the imprinted scales and to allow structure to grow fast enough afterward. Without dark matter, the early pressure of radiation would keep ordinary matter from clumping effectively until much later. The later universe would then be too smooth. The observed richness of structure suggests early help. Another scale shift arrives softly. The mottling is seen as tiny differences across the sky. The physical regions that create them are enormous, spanning tens of millions of light years in today's scale. A small patch in view corresponds to a vast region in space. The time also stretches. A signal is observed now. Its origin is hundreds of thousands of years after the beginning. The growth that follows continues for billions of years. The mind moves from a faint texture to cosmic history without strain. A limit of observation enters with clear gentleness. The pattern is extremely subtle. It can be confused with foreground emission from later cosmic material. Separating the primordial signal from later contamination requires careful modelling. Another limit is resolution. Very small-scale variations are blurred by the finite thickness of the last scattering surface and by diffusion of photons before release. This is a physical limit, not a failure. It sets a natural smoothing scale. A third limit is interpretation. Many cosmological parameters influence the same statistical features. Different combinations can mimic one another within bounds. This is a degeneracy of models. Even with these limits, the broad conclusion remains stable. The pattern strongly favours a significant dark matter component that contributes gravity early without coupling to radiation like ordinary matter does. Another small unlock comes from linking this to the earlier sections. Rotation curves show missing mass in galaxies. Lensing shows missing mass in clusters. The background glow shows that missing mass is not only a late-time patch, it is part of the universe's early composition. It shapes the initial conditions for everything that follows. Another visual anchor settles into calm. The sky's oldest light is a soft sphere of pale glow. Over it lies a mottled texture like faint breath on glass. The texture is gentle, yet it contains a blueprint. The section eases forward. The next movement looks closer at the preferred sizes within this pattern, where acoustic oscillations leave structured peaks that dark matter helps set. A calm pattern repeats across the oldest light like a slow rhythm that returns at familiar intervals. Those repeated scales come from early sound-like waves, and their imprint shows how dark matter sets the stage for structure. In that region, the mottled sky is not just random patches. Some patch sizes appear more often than others. The texture has a preferred grain. It is as if the sky carries a faint spacing between brighter and dimmer regions. The physical detail is the spacing itself. It feels like a gentle tiling with soft edges. The first small unlock comes from why spacing can exist at all. In the young universe, ordinary matter and radiation are tightly coupled. Radiation pushes outward, gravity pulls inward. This creates oscillations. The oscillations are not heard. They are patterns of compression and rarefaction in a hot plasma. Compression means regions squeezed denser. Rarefaction means regions stretched thinner. These alternating regions form waves. When the universe becomes transparent, the wave pattern freezes into the background glow. The sky then carries a record of where the plasma is slightly denser or slightly thinner at that moment. Another slow visual anchor settles on a single large region of slightly warmer glow. Around it, a faint ring-like feature can be imagined. The ring is not a sharp circle. It is a broad band where the pattern shifts from warmer to cooler and back. The next unlock is that such a ring corresponds to a sound horizon. Sound horizon means the maximum distance a pressure wave travels before the snapshot. It is a limit set by time and by the speed of sound in the early plasma. This single scale becomes a ruler embedded in the sky. Dark matter matters because it shapes the gravitational wells that drive the oscillations. It supplies pull without adding the same pressure response as ordinary matter. This changes how strong the compressions become compared to the rarefactions. It also changes how the pattern's preferred scales line up. The analogy shifts to something quiet and physical. A drumhead can hold standing waves when tapped, even when the tap is gentle. Some wavelengths fit the drumhead's size, others do not. The modes that fit become stronger and repeatable. In the early universe, the plasma behaves like a drumhead stretched across space. Gravity and pressure set the modes. Dark matter changes the tension of the system, not by stretching a surface, but by deepening the gravitational landscape beneath the oscillations. The analogy clarifies the idea of preferred modes. Certain sizes are favoured because the system has limited time to oscillate before the snapshot. Another slow visual anchor shifts to a set of ripples on a broad lake at dusk. The ripples overlap. Some patterns reinforce, some cancel. A faint grid of interference appears. The next unlock is that the background pattern can be summarized by how much variation exists at each angular scale. Angular scale means the size of a feature on the sky measured in degrees. Features can be large, spanning many degrees. Features can be small, spanning fractions of a degree. The distribution of power across these scales forms a series of peaks. Peaks are the favored modes. The positions and heights of these peaks are sensitive to the amounts of ordinary matter and dark matter. The peaks are not arbitrary. They are the quiet result of an early competition between gravity and pressure. A single number can hold the human sense of scale without introducing symbols. The most prominent preferred scale corresponds to about 1 degree on the sky. That is like the width of a thumbnail held at arm's length. The comparison is only a way to imagine size. It shows that the pattern is neither microscopic nor huge. It sits at a calm intermediate scale. This scale links to the sound horizon. It also links to the geometry of the universe between the snapshot and now. The next small unlock comes from how dark matter affects the wave pattern. Ordinary matter adds inertia to the plasma. More ordinary matter makes compressions deeper. Radiation pressure pushes back. Dark matter provides gravitational wells that remain even while the plasma oscillates. This means the plasma oscillates inside a pre-existing potential landscape. The compressions can become stronger at particular phases. The rarefactions can be weaker in a predictable way. The relative peak heights carry this story. Dark matter therefore leaves a signature in the pattern's rhythm. It does not need to shine, it only needs to pull. Another visual anchor becomes more concrete. Imagine a series of soft concentric bands across the sky. They are not perfect circles, they are statistical preferences. The bands correspond to different modes of oscillation that fit into the horizon size. The next unlock is that higher modes represent waves that have completed more oscillations before the snapshot. Some have only reached a compression phase, some have reached a rarefaction phase. The time available before transparency acts like a deadline. Only certain phases are captured. This is why the peaks appear as a sequence rather than a smooth slope. Dark matter influences how quickly the gravitational wells deepen and how much the plasma is driven into compression before the deadline arrives. This helps produce a pattern that matches observations. The scale shift arrives softly. A 1 degree feature is a small patch in view. Yet it corresponds to a physical distance in the early universe that is immense. That same distance later expands with the universe to become a much larger physical scale. The tiny patch on the sky becomes a ruler for cosmic history. A minute change in brightness becomes evidence about matter content on the larger scales. Another small unlock connects this to structure growth. After the snapshot, radiation no longer traps ordinary matter. Ordinary matter can then fall into the gravitational wells already seeded. Dark matter has already begun clustering. Its wells are deeper than ordinary matter could make alone at that time. This accelerates the growth of galaxies and clusters. The background peaks are therefore not just about the early plasma, they are about the entire later universe. They encode initial conditions and composition. Another visual anchor returns to the lake ripples now seen as they fade into stillness. The water calms. The interference pattern remains as a faint memory in the surface texture. In the same way, the plasma's oscillations end as the universe becomes transparent. Their imprint remains in the background glow. The limit of observation enters with calm clarity. The peaks are extracted from a subtle pattern. Foregrounds from later cosmic emission can distort the spectrum. Instrumental noise and beam smoothing can blur small-scale power. This is a resolution limit. Another limit is cosmic variance. The sky provides only one realization of the universe at the larger scales. Very large features are few in number. This sets a statistical uncertainty that cannot be beaten by longer observing time alone. A third limit is model dependence. Interpreting peaks requires a cosmological model that includes expansion history. Different parameter combinations can partially trade off. This is a degeneracy. Even with these limits, the fit that includes substantial dark matter remains strongly favoured. The sequence of peak positions and relative heights is difficult to match without a dark matter component that contributes gravity without coupling to radiation like ordinary matter does. Another small unlock appears as a quiet conclusion of the rhythm. The background pattern is a record of waves. The waves require gravity and pressure. Dark matter changes the gravity side of that balance early, then continues to guide growth later. The evidence is not a single peak. It is a coherent sequence that behaves like a signature. The section eases forward. The next movement leaves the early sky and follows the growth of structure, where dark matter forms a scaffold of filaments and voids that later hold galaxies like dew on threads. A vast web can be invisible in darkness, yet its strands are outlined by where galaxies prefer to gather. Structure growth follows gravity's scaffold and dark matter supplies most of that scaffold long before starlight appears. In that region, the universe is not a uniform fog. It is a network. Dense knots connect by long filaments. Between filaments lie voids that feel spacious and quiet. The physical detail is the filament itself. It is not a solid line. It is a gradient of density that thickens toward nodes and thins along bridges. The first small unlock comes from why a web is expected. Small density differences in the early universe grow over time. Gravity amplifies them. Regions that start slightly denser pull in more matter. This makes them denser still. Regions that start slightly thinner lose matter. This makes them thinner still. Over billions of years, this feedback produces a foam-like pattern of walls and voids. Ordinary matter alone struggles to begin this process early enough because early pressure resists collapse. Dark matter not coupled to radiation in the same way can start clumping earlier. It forms potential wells that ordinary matter later follows. Another slow visual anchor settles on a filament seen in projection as a faint bridge of galaxies. The bridge is not evenly bright. It has a thicker midsection where galaxies cluster more tightly. It has a thinner extension where the density fades. At the edges, the galaxy density drops gradually. There is no sharp boundary. The next unlock is that the visible galaxies are tracers. They mark where matter collects, but they do not represent the full mass. The filament's gravitational influence can extend beyond where galaxies are most obvious. Gas can also lie along the filament. Dark matter dominates the mass budget and provides most of the pull. This means the web is not built out of light. Light only decorates the densest parts. The analogy shifts to something quiet and tactile. A thin layer of frost can form along invisible cracks in a cold window pane. The cracks guide where frost gathers first. The frost makes the hidden pattern visible. In the same way, galaxies gather along a hidden gravitational pattern. The pattern exists even where the visible traces are sparse. The analogy clarifies a key point. The decoration is not the structure. The structure guides the decoration. Another slow scene moves inward toward a node. The node is a cluster. Galaxies are packed more tightly. A diffuse glow of hot gas fills the center. Around the node, filaments feed inward like slow streams. The physical detail is the layered density. The center is dense and bright. The outskirts are dimmer and more diffuse. The next unlock is that nodes form where filaments intersect. Matter flows along gradients. Over time, these intersections collect mass. Dark matter halos merge and grow. Ordinary matter falls into the deepening wells. Gas can heat as it compresses. The result is a cluster embedded in a web. This connects earlier evidence. Lensing detects mass in clusters and along filaments. Rotation curves detect mass in galaxy halos. The web ties those scales together. A single number can hold the timescale of this growth. The first galaxies begin forming within about 1 billion years after the beginning. That is like the first islands rising from a slowly lowering sea. The comparison is about emergence. It emphasizes that the web scaffold must exist early for galaxies to appear in time. Dark matter helps by forming wells before ordinary matter can cool and settle efficiently. The web provides the locations. Ordinary matter provides the glow later. Another visual anchor drifts to a void. The void looks like a dark basin. Few galaxies sit inside. The edges of the void are marked by thin sheets and curved walls. These walls are not rigid. They are broad regions where density is higher than the void interior. The physical detail is the boundary layer. It's a thick rim rather than a sharp edge. The next unlock is that voids also carry information. Their emptiness is not absolute. It is relative. Matter has moved outward toward filaments and nodes. This outward movement means gravity has been acting coherently across large scales. Dark matter, being most of the mass, drives this coherent flow. The shape of voids and their distribution depends on how matter clusters. This provides another check on dark matter models. Another scale shift arrives softly. A filament can be millions of light years long. Within it, a galaxy halo can be only tens of thousands of light years across. Within that halo, stars orbit on scales of thousands of light years. The same gravity connects these levels. The field is not the same strength at each level, but it is part of one hierarchy. A subtle density difference in the early universe grows into a filament. A filament feeds a cluster. A cluster contains galaxy halos. Halos contain rotating disks. The chain is continuous and calm. Another small unlock comes from the idea of bias. Galaxies form in dense regions first. This means galaxies overrepresent high-density parts of the underlying mass field. The mass field itself is smoother. Dark matter forms a web everywhere. Galaxies appear where the web is thickest. This explains why the visible universe looks clumpier than the total mass distribution. Weak lensing and the cosmic background can probe the smoother field. Galaxy surveys probe the biased traces. Together they build a consistent picture. A limit of observation enters with gentle clarity. The web is seen indirectly. Galaxies are sparse traces. Many regions between galaxies contain mass without bright markers. Projection can also confuse. A filament can appear denser if multiple structures overlap along the line of sight. A void can appear emptier if faint galaxies are missed. This is a sampling limit. Another limit is the modelling of how galaxies form within halos. Different formation histories can change how strongly galaxies trace the mass. This is a limit of inference. Even with these limits, the large-scale patterns are robust. The existence of a cosmic web is expected from gravitational growth. Its detailed statistics match a universe where dark matter dominates the clustering mass. Another visual anchor settles on the web as a quiet lace-like fabric. Nodes are thicker knots, filaments are thin threads, voids are open spaces between. The fabric is not solid. It is a gradient of density across immense volume. The presence of this fabric links the early background patterns to the later distribution of galaxies. The section eases forward. The next movement looks closer at the kinds of dark matter that can build this scaffold, and how different candidates change the sharpness of filaments and the density of small halos. A filament can look smooth from far away, yet its fine grain depends on what dark matter is allowed to do while everything is young. The sharpness of cosmic structure on small scales distinguishes slow clumping dark matter from faster smoothing varieties. In that region, the web is seen as a set of long bridges and dense knots. The bridges are not uniform. Some appear studded with small condensations. Others look like quiet threads with fewer interruptions. The physical detail is the spacing of these condensations. It suggests whether matter gathers into many small halos or only into larger ones. A halo is a bound cloud of mass held by gravity. The first small unlock comes from a simple link. If dark matter settles early into many small halos, later galaxies can form in more places. If dark matter smooths away tiny clumps, early fewer small halos survive, and the web's fine grain is softened. This difference can be traced back to the early universe when dark matter either stays locally confined or streams across small distances. Another slow visual anchor settles on a single galaxy halo far from any cluster core. Around the central glow, the surrounding space is not empty. It is filled with a faint, nearly spherical envelope of mass. Within that envelope, subtle knots appear at different radii. Some knots are small and compact. Some are more diffuse. The boundary of the envelope is not sharp. It fades outward in a gentle gradient. The next unlock is that these knots represent subhalos. Subhalos are smaller halos, orbiting within a larger halo. Their abundance depends on how readily dark matter clumps. A dark matter type that stays cold and slow can form many subhalos. A type that stays warmer and more mobile can erase the smallest ones before they ever become bound. This is not a matter of preference. It is a consequence of early motion. Another visual anchor shifts to a long filament viewed along its length. The filament resembles a dim rope of mass with brighter beads where density peaks. The beads are irregular in size. The spaces between them vary. The outer edge of the filament is feathered. It blends into a lower density background rather than ending abruptly. The next unlock is that the filament's bead pattern is an archive of early smoothing. If small fluctuations survive, they grow into many beads. If they are wiped out, the rope is smoother and only the biggest knots remain. A single concept can hold the mechanism without becoming heavy. Free streaming means particles travel far enough to blur small clumps. One sentence can define it plainly. Free streaming is early motion that smooths density on small scales. Two simple images can carry it. Fine dust carried by a gentle breeze spreads into a thin veil. Heavier grains settle into pockets and keep sharp edges. One sentence can state why it matters. Smoothing changes how many small halos exist later. The first small payoff comes from the role of speed. Dark matter that moves slowly in the early universe behaves like cold dark matter. Cold dark matter means slow-moving dark matter that clumps on very small scales. It preserves tiny seeds. Those seeds can grow into many small halos and subhalos. Dark matter that moves faster behaves like warm dark matter. Warm dark matter means faster dark matter that erases the smallest seeds. It produces a cutoff. Below a certain scale, structure is suppressed. The web is still present. The largest filaments and clusters still form. The difference lives in the fine grain. Another slow visual anchor settles on the edge of a void. The void boundary is a thick wall. Along that wall, faint galaxies appear in a loose chain. Between them there are long, quiet gaps. The wall itself is not uniform. It has slight folds like layered curtains of density. The next unlock is that void boundaries are sensitive to small-scale power. If many small halos exist, the wall can be more textured. If small halos are missing, the wall can look smoother and more continuous. This offers a way to distinguish candidates without needing rare alignments or special systems. The scale shift arrives gently. The same dark matter property influences structures as small as dwarf galaxy halos and as large as the cosmic web. A subtle early velocity distribution sets a pattern that persists across billions of years. Tiny differences in the early density field become the difference between many small clumps and a smoother landscape. The mind can move from a single halo substructure to a filament spanning millions of light years without strain. A single number can anchor the idea of small scale in a calm way. A dwarf galaxy can be about 1,000 times less massive than a large spiral galaxy. That is like comparing a small pond to a great lake within the same valley. The comparison is only about relative scale. It emphasizes that dwarf halos live near the threshold, where smoothing effects become important. If the smallest halos are suppressed, the faint end of the galaxy population changes. If they survive, the universe can host many more small dim systems. Another payoff follows from how evidence connects. Rotation curves reveal dark mass in single galaxies. Lensing reveals dark mass in clusters and along filaments. The cosmic microwave background reveals early conditions. Small-scale structure tests how dark matter behaves between those anchors. It checks whether the same dark component that fits large-scale evidence also produces the correct fine grain. This is where candidates can diverge while still matching the broad picture. Another slow visual anchor returns to the halo envelope around a galaxy. The envelope's inner region is smoother. The outer region shows a faint, uneven texture. Some subhalos appear as gentle density bumps rather than sharp peaks. Their edges are soft. Their centers are not infinitely dense. The next unlock is that internal profiles also matter. Some models predict cusps, meaning steep central rises in density. Some predict cores, meaning flatter central regions. This is a detail of how dark matter clusters and whether additional physics is present. The clue is physical shape. A cusp would create a sharper central gradient. A core would create a gentler one. These shapes influence how stars and gas move in the inner parts of small galaxies. Another payoff comes from an important caution. Ordinary matter can also reshape inner profiles through processes that move gas in and out over time. Even without describing any human work, the consequence is clear. The inner structure of a halo is not a pure dark matter signature. It is mixed with complex ordinary matter behavior. This makes the evidence subtle and requires care. A limit of observation enters softly and specifically. The smallest halos can host very little light. Their signals would be faint and easy to miss. Some halos might contain no visible galaxies at all. Their presence would need to be inferred indirectly through their gravitational influence. Another limit is modelling. Separating the impact of dark matter properties from the impact of ordinary matter requires assumptions about how galaxies form in small halos. This is a limit of inference, not a reason to stop. It means multiple lines of evidence are needed. Despite these limits, the small-scale pattern remains a powerful discriminator. Warm-like dark matter smooths and reduces the smallest halos. Cold-like dark matter preserves them. Ultralight wave-like candidates can behave differently again. The section eases forward. The next movement turns from the web's fine grain to the leading candidate families where mass interaction, strength, and even wave behavior set distinct cosmic fingerprints. A halo can seem like a simple envelope, yet its inner texture may be set by whether dark matter behaves like grains or like waves. Leading candidates produce the same large-scale gravity, but they leave different small-scale fingerprints. In that region, a galaxy halo is imagined as a faint sphere of influence. Its density is not uniform. It rises inward. It falls outward. The fall is gradual, like a dimming gradient rather than a cliff. Within the halo, small ripples in density can appear as gentle bumps. The physical detail is the ripple edge. It is soft and rounded, not sharp. The first small unlock comes from a straightforward split. Some candidates behave like massive particles that cluster in the usual way. Others behave like extremely light fields that act like waves on galactic scales. Both can be dark, both can be long-lived, both can dominate mass. Yet they differ in how tightly they can pack into small regions. A second unlock follows from the concept of interaction. Some candidates rarely interact except through gravity. Some may have slight self-interactions that allow energy to redistribute within the dark component. These differences can alter the inner shape of halos and the survival of substructure. Another slow visual anchor settles on a small dwarf halo. The inner region is not a sharp spike, it is a calm plateau. The density appears nearly constant across a central core. Around that core, the density begins to fall. The transition is smooth. The next unlock is that a chord profile can arise in more than one way. One path is wave-like behavior from ultralight candidates. When dark matter has a long wavelength, it cannot be confined to arbitrarily small scales. It forms a central soliton-like core. Soliton-like means a stable, wave-supported lump. One sentence can define a key term in a simple way. Quantum pressure is a wave effect that resists extreme compression. Two sentences can anchor it with imagery. A stretched sheet can resist being pinched into a point. A water surface can smooth tiny ripples into broader swells. One sentence can state why it matters. This smoothing can reduce the number of very small dense subhalos and soften halo centers. Another slow visual anchor shifts to a larger halo, where faint interference-like texture appears. The halo is not perfectly smooth. It shows subtle banding. The banding is not a ring. It is a set of faint overlapping ripples that drift and fade. The next unlock is that wave-like dark matter can create interference patterns. These patterns can add a grainy, time-varying density field on small scales. Even without describing any direct measurement, the consequence is clear. Stars and gas would respond to a slightly fluctuating potential. Over long times, this could heat or stir the inner parts of small systems. The effect is gentle. It is not a violent shake. It is a persistent background of soft fluctuations. The analogy shifts to a quiet light pattern. Moonlight passing through a thin curtain can create faint bands on a floor. The curtain is still. The bands are soft. Small changes in the fabric can shift the pattern. In the same way, a wave-like dark component can project a subtle interference texture into the gravitational potential. The analogy clarifies the feel without adding any human presence. It is about soft patterning rather than hard collisions. Another unlock follows by contrasting with particle-like cold dark matter. Particle-like cold dark matter naturally makes many small halos and cuspy centers. Cuspy means density rises steeply toward the center. It also predicts abundant subhalos. These subhalos can persist as small bound clumps within larger halos. This fits large-scale structure well. It may create tension on the smallest scales depending on how ordinary matter reshapes inner regions. This is where self-interacting dark matter enters as a candidate family. One sentence can define it plainly. Self-interacting dark matter has dark particles that scatter off each other slightly. Two sentences can anchor it with imagery. A crowd of slow-moving grains can bump and share energy. Over time, the crowd spreads and smooths its densest spot. One sentence can state why it matters. Small scattering can turn a cusp into a core without erasing large-scale structure. A single number can anchor how subtle such interactions must be, without leaning on symbols. A typical dark particle in these models might travel billions of years and scatter only a few times. That is like crossing an ocean and only brushing past a handful of drifting leaves. The comparison is about rarity. It shows why the dark component remains effectively collisionless on large scales, while still having a chance to reshape dense centers. Another visual anchor returns to a cluster-scale halo. The center is dense, the outskirts are broad. Substructure appears as small bumps in the projected mass. The bumps are numerous, yet the overall field is smooth. The next unlock is that different candidates can produce similar cluster lensing on large scales. The divergence is strongest in small halos and inner profiles where wave effects or self-scattering can matter. This sets a strategy. Use large-scale evidence to confirm dark matter's presence. Use small-scale evidence to constrain its nature. Another scale shift arrives softly. Candidate physics can be microscopic in origin, yet its imprint appears in the shape of a dwarf galaxy core, or the count of subhalos along a filament. The same physics also influences the cosmic web's fine grain and the earliest background patterns. A tiny change in particle mass or interaction strength can ripple outward into cosmic history. Another small unlock follows from the role of ordinary matter. Gas cooling star formation and feedback can also create cores or reduce central densities. This means a core is not an automatic signature of exotic dark physics. It is a shared outcome with different causes. This is where combining evidence becomes essential. Lensing can find substructure even when light is absent. The cosmic background can constrain early smoothing. Galaxy counts in voids and filaments can probe small halo abundance. Each line narrows the allowed space. A limit of observation enters with calm specificity. The smallest halos may carry little or no light. Their presence must be inferred through subtle gravitational effects. Those effects can be weak and hard to separate from projection and noise. Another limit is degeneracy. Different dark matter models can produce similar halo cores when ordinary matter is included. Disentangling them requires multiple systems and consistent patterns across environments. A third limit is time. Wave interference patterns evolve. Any long-term effect must be extracted as a statistical imprint rather than a snapshot. Despite these limits, the candidate landscape is not shapeless. Cold particle-like behavior favors abundant small structure. Warm-like behavior suppresses the smallest halos. Ultralight wave-like behavior creates core structures and interference texture. Self-interactions can soften centers without large-scale smoothing. The section eases forward. The next movement turns to how these candidates can be tested through indirect signals in the sky, where annihilation or decay could leave gentle traces without requiring direct contact. A faint excess of light could emerge from deep space not as a beacon, but as a gentle imbalance in how often certain photons appear. Indirect signals search for rare dark matter processes, and their silence can be as informative as a detection. In that region, the scene begins with a quiet halo around a galaxy. The halo is broad. It has a denser inner region and a thinner outer skirt. The density falls with radius in a smooth gradient. Near the center, the gravitational well is deepest. Farther out, it becomes shallower. The physical detail is the steepness of that gradient. It shapes where any signal would be brightest. The first small unlock comes from a simple idea. If dark matter can annihilate or decay, it can produce standard particles and light. Annihilation means two dark particles convert into other particles. Decay means one dark particle transforms over time. Both processes would be rare, both would be subtle, yet both would be tied to where dark matter is densest. This immediately explains why galaxy centers and clusters are often considered promising. The signal strength can scale with density. For annihilation, it can scale with density squared. For decay, it can scale with density. This difference is crucial. It changes how sharply the brightest region is expected to stand out from the rest. Another slow visual anchor settles on the central region of a halo as a soft glow layer. The center is not a point. It is a volume with a thickness. Within it, the density rises inward. If the profile is cuspy, the rise is steep. If the profile is chord, it is flatter. The next unlock is that the inner shape of the halo sets the expected concentration of any annihilation signal. A cusp would concentrate it strongly toward the center. A core would spread it more gently. This means that halo profile uncertainties directly become signal uncertainties. Indirect searches therefore depend on both particle physics and astrophysical structure. The analogy shifts to a quiet, candleless room. A faint scent released in one corner spreads outward. If the release is constant and steady, the concentration is highest near the source. If the room has gentle currents, the scent can disperse and flatten. In the same way, a dark matter signal depends on where the source term is strongest and how the distribution spreads with radius. The analogy clarifies the difference between a sharply concentrated source and a diffuse one. Another slow visual anchor moves to a cluster environment. The cluster halo is immense. Subhalos are embedded within it like small lumps within a larger cloud. The cluster's mass distribution is layered. The center is dense. The outskirts are broad. The next unlock is that substructure can enhance annihilation signals. If many subhalos exist, they add extra high-density pockets. This can raise the total annihilation rate compared to a smooth distribution. This boost depends on the number and concentration of subhalos. It therefore depends on whether dark matter is cold, warm, or wave-like. A smoother dark matter model yields fewer dense subhalos and less enhancement. A clumpier model yields more. The indirect signal idea becomes a test of structure as well as of particle properties. A single number can anchor the concept of rarity without forcing detailed particle masses. Some candidate particles could have lifetimes longer than 1 trillion years. That is like a mountain persisting through countless seasons, barely changing from one year to the next. The comparison is about longevity. It explains why decay can be incredibly slow and still matter on cosmic timescales. If the lifetime is enormous, decay is still rare. Yet over the vast amount of dark matter in the universe, the total number of events could still be non-zero. Another payoff follows from the role of spectral shape. Annihilation or decay could produce photons with characteristic energies. The pattern might appear as a broad continuum or as a sharper line. The line would be particularly distinctive because astrophysical backgrounds rarely produce perfect lines. Yet natural broadening and propagation can smear even a line. Photons can scatter or be absorbed. Secondary particles can produce photons later through cascades. The expected spectrum depends on the final states and on the environment. Another slow visual anchor settles on a long line of sight through a halo. The line crosses regions of different density. It passes through the denser inner parts. It continues through the outer skirt. The next unlock is that indirect searches integrate along this line. The observed brightness would be a superposition. A signal would not map one-to-one to a single radius. It would be an accumulation along depth. This makes interpretation subtle. A bright patch can arise from a dense center. It can also arise from overlapping structures along the line of sight. This is why regions away from bright astrophysical emission are also considered. The aim is to reduce confusion from ordinary sources. Another scale shift arrives softly. The processes being considered happen on microscopic scales. A single annihilation is a tiny event. Yet the observable consequence would be a faint glow spread across degrees of sky. The chain from micro to macro is long but coherent. A particle property sets a rate. A halo profile sets a distribution. A line of sight sets an integral. The result is a map of faint brightness that can be compared across many targets. Another small unlock comes from the power of non-detection. If a signal is not seen where it would be expected for a given model, that model is constrained. This is not failure. It is refinement. It narrows the range of interaction strengths and lifetimes. It can also favor dark matter candidates that are truly inert except for gravity. The silence itself becomes a data point. Another visual anchor returns to a dwarf galaxy halo. The dwarf is faint. It has little ordinary emission compared to large galaxies. Its dark matter fraction is high. The halo is compact. The density can be significant in the inner region. The next unlock is why dwarfs are appealing targets. They can be relatively quiet in astrophysical backgrounds. If a signal appears there, it is harder to attribute to ordinary processes. If no signal appears, the constraints can be strong because the expected background is low. Yet even dwarfs carry uncertainties. Their inner density profiles can be chord or cuspy. Their substructure content is uncertain. The limit of observation enters with gentle specificity. Backgrounds exist across the sky from many ordinary processes. Their spatial distribution can mimic a dark matter profile in some cases. Separating them requires modeling. This is a limit of inference. Another limit is instrumental. Energy resolution and sensitivity can blur spectral features and hide faint lines. This is a resolution limit. A third limit is astrophysical structure. The true dark matter distribution in targets is not directly measured. It is inferred from traces. Errors in that inference propagate into signal predictions. Despite these limits, indirect searches remain valuable because they connect candidate physics to observable consequences. They also connect with structure evidence. Subhalos and cusps matter more for annihilation. Broad distributions matter more for decay. Wave-like smoothing and warm suppression reduce small-scale boosts. Each candidate family leaves a different expectation for where the sky would glow faintly and how that glow would scale from dwarfs to clusters. The section eases forward. The next movement steps back from specific signals and considers the broader cosmic consequences of dark matter, including how it shapes the history of galaxies and the timing of structure across the entire universe. A galaxy can look settled and still carry faint scars of a long assembly. Dark matter sets the timing and pathways of that assembly, and the visible universe largely follows those hidden tracks. In that region, a quiet spiral disk hangs like a thin blade. Around it lies a wide halo of darkness. Within the halo, faint arcs of starlight curve in long loops. Each arc is a tidal stream. It is a stretched ribbon of stars drawn out by gravity. The physical detail is the stream edge. It is sharper on one side and feathered on the other. The first small unlock comes from what the ribbon implies. A smooth halo is not smooth in history. Smaller systems fall in over time. Their stars are pulled into long curving bands. Their dark matter spreads more widely and merges into the host halo. This is hierarchical growth. It means large halos form from many smaller ones. Another slow visual anchor settles on one stream as it wraps halfway around the galaxy. Its brightness fades along its length. Its width changes from a thin thread to a broader veil. The next unlock is that dark matter governs how often such events occur and how early they begin. If dark matter clumps efficiently, many small halos form early. They provide more opportunities for accretion and merging. If small-scale structure is suppressed, fewer small halos arrive. The halo's outskirts can look quieter. The number of streams and their thickness then shift. This links candidate behavior to present-day structure, without relying on rare dramatic events. The analogy becomes calm and physical. Snow blowing across a plain gathers around stones. Some stones produce sharp ridges and narrow tails. Others produce broad drifts with softer edges. The wind is steady. The pattern accumulates slowly. In the same way, gravity shapes the distribution around mass. Dark matter supplies the mass that sets the flow lines. Ordinary matter traces the resulting ridges and tails. The analogy clarifies that the pattern is an archive of persistent shaping, not a single moment. Another payoff comes from the timing of collapse. In that region, the early universe begins nearly uniform. Tiny variations grow for a very long time. About 13 billion years pass like a shoreline, receiving countless gentle tides without ever stopping. The comparison is about repetition and patience. It explains why small differences can become large structures without any sudden step. Dark matter accelerates the first stage by clumping, while ordinary matter is still pressure supported. That early head start changes when the first halos appear. It changes when gas can begin to cool into dense regions. It changes the pace at which galaxies can assemble. Another slow visual anchor moves outward from the galaxy to the surrounding web. A filament approaches like a dim lane. It thickens near the galaxy group. The density rises in a gradient. Small companions sit along the lane like beads spaced at uneven intervals. The next unlock is that the web acts like a delivery map. Matter falls along filaments toward nodes. Halos receive material preferentially from certain directions. This can leave an isotropic structure. The outer halo can be slightly flattened along filament directions. Streams can align with those inflow paths. The effect is not a perfect symmetry. It is a statistical preference. Over long time, repeated infall along similar directions can imprint a gentle shape. The physical detail is the halo's ellipticity. It is not a sphere. It is slightly stretched, and the stretch changes with radius. Another payoff follows from concentration. Halos that form earlier tend to be more concentrated. Concentration means more mass packed toward the center relative to the outskirts. Early formation gives more time for matter to settle into deeper potentials. Late formation leaves a puffier distribution. This changes rotation curve shapes. It changes lensing strength near the center. It also changes the survival of substructure. More concentrated halos can hold onto subhalos more tightly in the outer regions. Less concentrated halos can be more easily stripped. The galaxy's visible disk sits inside these differences as a thin, luminous layer. The dark halo remains the main mass reservoir that sets the background field. Another slow, visual anchor returns to the inner halo. The density gradient is steepening inward. In a cuspy case, the rise is rapid. In a chord case, it is gentler. The next unlock is that this inner shape influences the stability of the central region over time. A steeper gradient can confine orbits more tightly. A flatter core spreads the central mass and changes orbital frequencies. Over billions of years, these differences affect how streams phase mix and dissolve. They affect how long coherent arcs remain visible. They also affect how sensitive the inner region is to small fluctuations from substructure or wave interference. The halo's memory is written in both its global profile and its fine grain. A limit of intuition arrives softly. It is tempting to treat a present-day halo as a direct photograph of the past. The past is not directly observed. Only a snapshot exists at any given time. Streams can overlap in projection and blend into a diffuse glow. Some can be too faint to separate from the galaxy's outer light. Subhalos can be present without any luminous traces. Their influence is inferred from subtle perturbations in streams and distributions. This is a limit of inference and contrast. It is not a lack of structure. It is a limit in how cleanly the structure can be read. Another payoff follows from statistics. While a single galaxy can mislead ensembles, reveal patterns. The abundance of small galaxies in filaments and around hosts connects to small-scale structure. The typical shapes of halo outskirts connect to anisotropic infall. The distribution of stream widths and lengths connects to merging history. These patterns are softened by ordinary matter processes, yet the broad gravitational scaffold remains. Dark matter's key consequence is that it makes a universe where structure grows early and grows hierarchically. That consequence threads through rotation curves, lensing the cosmic background and the web itself. Another slow visual anchor eases outward again. A group of galaxies sits in a shared halo. Between them, faint bridges of diffuse light stretch as soft sheets. The sheets have curved boundaries and gradual fades. The next unlock is that group environments magnify the same story. Interactions among halos and their substructure become more frequent. Material is stripped and redistributed. Dark matter binds the group and holds the broad potential. Ordinary matter responds by forming bridges and tails. Over time, the group can settle into a more relaxed configuration. Yet the outer halo continues to receive new material from filaments. The story is ongoing, but its pace is slow. The section settles into quieter tones. The next movement turns toward a gentle resolution, where the various lines of evidence align into a stable picture and ease into stillness. A stable picture can form from many soft clues, like a landscape revealed as fog thins without ever fully lifting. Dark matter evidence rests on patterns that agree across rotation lensing and the earliest light. In that region, the scene is wide and quiet. A spiral galaxy turns with a smooth outer disk. Beyond the disk, a halo extends into darkness. Farther still, a filament in the cosmic web fades into the distance. The physical detail is a gentle curvature in the disk's rotation. The curve does not fall as fast as visible mass alone would suggest. The first small unlock is the shared logic behind all lines of evidence. Gravity responds to total mass. Light reveals only part of that mass. Where motion stays fast at large radius, extra mass is implied. Where light bends more than expected, extra mass is implied. Where the cosmic background shows specific fluctuation scales, extra mass is implied. These are different scenes. The same conclusion repeats in calm agreement. Another slow visual anchor moves to a cluster halo. The cluster is not a point. It has layers. A denser core sits within a broader envelope. Around it, faint distortions of background galaxies form arcs and stretched shapes. The next unlock is that lensing provides a map that does not depend on how bright matter shines. It responds to gravity directly. The mass map often extends beyond the visible light. It shows smooth components and also substructure. This supports the idea of a dominant non-luminous mass component. Another visual anchor drifts toward the early universe. The cosmic background is a near-uniform glow. Its tiny variations form a delicate grain. The grain has preferred angular scales. The next unlock is that those scales act like a fossil of competing effects. Pressure in ordinary matter resists compression. Gravity from total matter promotes it. The pattern indicates that ordinary matter is not enough to shape the observed peaks alone. A non-luminous matter component helps build structure without adding the same pressure signatures. Another scale shift arrives softly. A single orbit in a galaxy takes a few 100 million years. That is like watching a slow tide complete one long cycle across a shoreline. The cosmic background, by contrast, is a snapshot from very early times. Between these two, about 13 billion years stretch like an unbroken night. The same gravitational rules apply across that span. The evidence is stitched across time. Another small payoff comes from the coherence of the cosmic web. Filaments and nodes appear in a characteristic network. Large-scale clustering matches, expectations for a matter component that does not stream too freely at early times. This supports cold-like behavior on large scales. Yet the small-scale story remains open in detail. The abundance of tiny halos, the inner density shape, the degree of substructure. These details are where different candidates still differ. Another slow visual anchor settles on a dark halo profile. The density falls with radius in a smooth gradient. The slope changes from inner to outer regions. The next unlock is that halo shape can connect the micro to the macro. A particle that is too warm erases small-scale structure. A wave-like field smooths dense cusps into cores. A self-interacting model can redistribute inner mass and soften central gradients. These possibilities do not erase the main evidence. They refine it. They suggest that dark matter is not a single monolithic idea. It is a family of hypotheses constrained by many observations. The analogy becomes gentle and unique. A quilt is assembled from different fabrics. Each patch has its own weave and thickness. Yet the quilt as a whole provides the same warmth. Rotation curves are one patch. Lensing is another. The cosmic background is another. Structure growth is another. The quilt's shared function is the gravitational effect of unseen mass. The differences between patches are the details that still invite careful study. Another payoff comes from what is not required. No single measurement needs to be perfect. The overall picture stands because the evidence is redundant. If one target is messy, others remain. If one galaxy is unusual, ensembles still trend. If one cluster is complicated, lensing across many systems still indicates extra mass. This redundancy stabilizes the conclusion. Another limit of observation arrives, stated softly. Dark matter is inferred, not directly seen. The inference uses models of baryonic physics, halo profiles, and background populations. Uncertainties remain in the inner regions of galaxies where ordinary matter can reshape halos. Confusion remains in indirect searches where backgrounds can mimic faint signals. Instrumental limitations remain in resolution and sensitivity. These are specific limits. They do not erase the gravitational evidence. They limit how precisely candidate properties can be pinned down. Another visual anchor returns to a quiet dwarf galaxy. Its light is faint. Its stellar distribution is compact. Around it, the gravitational field implied by motion is more extended than the light. The next unlock is that dwarves are small laboratories. They can sharpen constraints on small-scale behavior. They can test whether cores are common. They can test whether substructure leaves subtle effects. They can also show where baryonic influence is minimal. This makes them calm yet powerful guides. Another scale shift eases outward again. From a dwarf to a spiral. From a spiral to a cluster. From a cluster to the web. The same invisible scaffold persists at every step. It shapes how matter gathers. It shapes how light bends. It shapes the rhythm of growth across cosmic time. In that region, the sense of mystery softens into a steady framework. The universe appears not as a riddle demanding an answer at once, but as a landscape where many paths converge. The final visual anchor is the cosmic web seen as a dim lattice. Filaments connect nodes with gentle thickness gradients. Voids open as broad, quiet basins. The pattern is stable on vast timescales. The closing unlock is that dark matter is not introduced as a dramatic object. It is inferred as a consistent accounting of gravity. It explains why galaxies stay bound at their edges. It explains why lensing maps extend beyond light. It explains why early fluctuations grow into the structures seen later. The candidate question remains, yet the evidence base is steady. The transition now becomes a soft landing. The scene holds its stillness. The web fades into darkness. The remaining motion is slow and rhythmic. The next moment does not ask for more. It simply lets the large-scale structure remain quiet and complete.